I trust everybody. All right. Pull this over there. Looks like there's still a couple of you. You certainly would. You put I. You can go ahead and put these away. Yes. What can I do for you?
You're missing something. These are I thought they were non-reactions because these both are.
All right, what?
Precipitates, and these are both soluble.
This is a precipitate, and that is a precipitate.
That
There.
one there doesn't say anything.
PO4 is always insoluble except with those things.
And it's not one of those things.
Yeah, those things make it insoluble, or make it soluble. So it's always insoluble unless it's with one of those. It's not with one of those, so it is insoluble. Same with hydroxide. So you're just reading the chart a teeny bit wrong.
I just read it wrong.
All right. I feel like this is a lot better than the 31% average you had on the other time we used this. So that's progress, right? By a lot. You're right, 24%. That's like unbelievable progress.
That will get you up from a B plus. Some of that number
Sure.
5 is going to be right.
I already fixed number 5.
Or an F2 like a D plus.
Oh, that's dumb. I did fix it, and it shows on your scores, but it still keeps it at 0. That's kind of dumb. All right. These 3 people. Oh, I got you. Yeah, number 5. Sorry, I fixed number 6 is when I fixed.
So those people only miss number 5?
Yeah.
Wow.
3 people only missed 1. So good job. Let's go ahead and reteach this. Make sure we're nice and solid here. When solutions of sodium chloride and lead 2 acetate react, what is the precipitate? All right, I don't know if this will work because I'm still not very comfortable with it. But we have NaCl plus PbC2H3O2, 2, right? Goes to, I don't want to write the whole thing out. I know that sodium and I know that acetate never form anything, so I would just double check to see if PbCl2 would. Chlorine is always soluble except when it's with lead, mercury, and silver. Is there another one I could? So this would be solid. So lead 2 chloride.
What's up with the first answer and the third answer? Yeah. The exact same thing, but wrong.
That's a great question.
One was L's. Do you guys use L's?
Probably not.
Or like 1?
I have no idea.
I use capital I.
So that's even better. 66% got that right. All right, this person, this is actually, well, yeah, it's probably one person. Not bad. Don't forget the Roman numeral. These 3 or 4 people, there definitely is a reaction. Dead giveaways, if lead's involved, you probably are going to have a precipitate that involves lead. All right, I don't know if this will scroll or what. Oh, sweet. Let's see if I can figure this out. So, clear ink. There we go. Potassium nitrate and acetate. This should have been a super easy one, and it was. 80% of you got this right. If you see nitrate and acetate, neither one of those form a
I
precipitate.
wrote it and then I was like, why did I write that?
Yeah, that's a ton of work for nothing. Okay?
I wrote,
The better you know your solubility rules, the more time you can save. We all right with that?
what's the chemical compound for acetate?
C2H3O2.
Okay.
All right, then we'll scroll. I got to clear that again. Number 3, when solutions of potassium hydroxide and zinc nitrate, so we have KOH plus ZnNO3 2. Why is there a 2? Because zinc's always a plus 2, right? Kind of a pain, but it just always is. All right, I know that this will not form. So K and NO3 probably not. So what I'm left with is zinc hydroxide. And I would check my solubility rules. This is probably a mistake, but whatever. Hydroxide is right here. Hydroxide is always insoluble, meaning it always forms something solid, except if it's with these things. If it is with one of those, it is soluble or is not part of the precipitate. Since we had zinc hydroxide, it did not have one of these, so it is insoluble. So that's my solid, zinc hydroxide. Got to come back. 87%, that's really super good. So didn't even need to do that one. All right, 67% got this one right. Oh, I thought you were going to scroll, but that's okay. When solutions of ammonium phosphate and calcium chloride react, what is the precipitate? Ammonium never forms a precipitate, right? All right, so it's not going to be ammonium chloride because that would be the other half. So I would be looking at calcium and phosphate. So I would do the same thing. I would see PO4 is always insoluble except for some things, but calcium is not one of those things. Calcium phosphate. 67. What's wrong with this? And not being mean, but what's wrong with this?
They're both positive.
All right, they're both positive. Don't put those together. Okay, they would repel each other. Okay, number 5 is a tricky question. I don't know if anyone got it right. Well, you said it would go down. All right, so this person got it right. Is that you, Windsor?
You go down.
I wasn't going to put a whole paragraph like that because then I was judging me.
This person is perfect. We'll balance out the conductivity so it is 0 again because 1 is oh, well.
They're both products. Go down to mine.
They're kind of right.
What? That's my favorite. Who did what? Who did what?
This one's really close.
Dang, what did I miss?
It doesn't really have anything to do with pH, but it's really, really close.
Makes sense though.
Kind of. All right.
Somebody used the wrong way.
That's all right. So 1 molar sulfuric acid was added to 1 molar barium hydroxide, yada, yada, yada. It's a little bit complicated, but not too bad overall. Oh, we're in trouble. Hold on. Let me get my recording to do something besides show a black screen.
Don't they both form?
They do, sort of. I don't know what's going on here, but oh well. Luckily we have next hour. All right, here we go. Stick with me. The answer is no, they don't both form precipitates, but they both form something. So we have H2SO4 plus BaOH 2 goes to BaSO4 plus HOH. All right, now I would check, is this soluble in water? No, it is not. This is a solid precipitate. What is this? That is water. Does electricity conduct in pure water? No. Does this stuff provide ions to the solution? No. So the answer was decrease because both products are not electrolytes. So what you actually will see, you'll see a white kind of cloudiness go in, and if your conductivity probe is like that light bulb I have, it'll get really dim, it will shut off eventually, and then it goes right back on. Why would it go right back on? What would that mean? All right, this demo is really hard to do because your conductivity goes like this. It's because if you go past this point where you have exactly the right amount of moles of each, then you have just extra H2SO4, SO4. And that is a very strong electrolyte, if you remember. So it'll be bright, dim, off, dim, bright, right back at you. All right, next up, oh, Tom. Oh boy. I can walk. I have this right over here. This is what happens when I try to get techie. Well, if the new computer would work with the newer slate, life would be fine. But for some reason, it only works with the 10-year-old slate instead of the 4-year-old slate. Okay, I did fix this. I don't know why I just put fluoric, but I did. I fixed it to fluoric acid to make people not hate me. Fluoric acid is the correct answer. Yeah, that person just spelled it a little teeny bit wrong. So this is just straight memory. There's nothing real hard about this besides you just have to memorize that fluoric acid is not considered a strong acid, and neither is hydrofluoric acid, because fluoric acid isn't really, that's not really a thing. But if it's not a thing, it's certainly not a strong acid. Nitric acid, very strong. Bromic acid, strong. This is fine, because that's how I had it. Sulfuric, strong. Spelled wrong. Bromic, strong. Number 7, which is not considered a strong one, it is magnesium hydroxide, because strong bases, they live in family 1 or the bottom 3. We ignore radium, so CASRBA. Did anyone spell magnesium wrong? Nope.
I don't know how. It's like up there.
I know. It happens. Okay, overall, especially if we have this one fixed up and a couple others, I thought we did just fine. Should stay on projector mode, hopefully. So, not bad. Not great. This person was really fast. Anyway, questions about that? All right, we're going to move on then to did we already talk about acids and bases much in this class?
Yeah.
Whoops, what did you just do, Tom? All right. For some reason, when that's full screen, it doesn't fit. So we go part screen. You can just imagine my cute kids behind there. All right, we're going to fly through a couple of things today, and then we'll start mathing stuff pretty soon, but not today. All right, so we just actually talked, and I imported this. I have no idea why it looks so terrible. Sometimes it imports things normal size, and sometimes it makes them super tiny. Apparently, making that larger is not an option. So whatever. I'll just tell you. It says in an acid-base reaction, the acid donates H plus to the base. Oh, there you go. Like, it's not even all there. Look at that. That's the box that fills. This is fun. I could do this all day. All right, so the H plus donates the acid donates the H plus to the hydroxide, and that's just going to form us some water. A neutralization reaction, this was one we just barely did, and I don't know why when I import it, it turns out with these weird things, but it does. This is just an arrow. So hydrochloric acid plus NaOH goes to NaCl plus H2O. What would happen to the conductivity of this solution over time? What would your best guess be? What? Well, it neutralizes, but what about the brightness of the light? Okay, well, it doesn't get brighter, it actually just stays the same. Because beforehand we had strong electrolytes, after we have strong electrolytes. So really, it's going to stay pretty much the same. The only reason the one in the quiz changed is because this thing was not aqueous, it was a solid. All right, so when solutions of acid or base are combined, the products are a salt and water. Hopefully you've read this. Next, I have no idea what's happening again. When a strong acid reacts with a strong base, the net ionic equation is always super duper simple. It's always H plus, oh, this thing's driving me nuts, plus OH minus goes to HOH. That's the net ionic equation for this, because if it came from a strong acid and a strong base, then the other two things are strong electrolytes, so Na plus, Cl minus, they're not together. Those are called spectator ions. You okay with that? So they would cancel out, and we're just left with pure water. I feel like this is the same thing over and over. Neutralization reactions. Observe the reaction between milk of magnesia, MgOH2, and HCl. I don't know. Yada, yada, yada. Milk of magnesia. You don't need to write this or anything. But that's a medicine you take for heartburn or a stomach ache. So you drink that, and it's MgOH2. It goes into your stomach, which is pretty much the same as hydrochloric acid. If hydrochloric acid is a strong acid, it really means you have Mg. Remember, this is white. That proves that MgOH2 is what? It's insoluble. Okay, now they can, if you've ever had milk of magnesia, it's just a pasty, gross tasting white liquid. Yeah, that stuff. All right? That white stuff is the magnesium hydroxide. Like, you can put it into water, but it doesn't really dissociate. But once it goes down to your stomach, you have the H plus and the Cl minus in there. This will react with that to form MgCl2 plus HOH. Neither one of these hurt your stomach. so you feel a little bit better. All right? I don't know. There's your biology for a second. Speaking of your belly, gas-forming reactions. All right. I'm going to put a star here. AP test loves these. Okay, these metathesis, or as I call them, double replacement reactions, do not give the product expected. The expected product decomposes to give the gaseous product of carbon dioxide or sulfur dioxide. There are not very many of these, so it's not super hard. If you have a metallic carbonate plus an acid, you would think that it would form H2CO3 and CaCl2, which it kind of does, but it decomposes. To me, this looks horrible to write, so let's just draw this out together. So here we go, once again. So calcium carbonate, and this would be a solid, plus my hydrochloric acid. So you would think just complete molecular, whatever we want to call it, it should be CaCl2 plus H2CO3. That would make sense to everybody, right? All right, and it kind of is. It forms CaCl2, but this substance right here is an unstable acid. Unstable is really the right word to say. So it breaks into two parts. It breaks into water plus this gas of CO2. So the key for your first, can't change colors. That's what I was hoping that would happen. It won't even let me go to that corner. I didn't want to anyway. Luckily, I brought my mouse over here. All right, I just wanted to select the different color. This is dumb. All right, so the first one that you should commit to your brain is that metallic. Oh, great. All that work for nothing. Carbonates and acids produce carbon dioxide. And if you ever see this symbol, that always means and to me, whether it's rounded out or not. That's an and sign. That's a B flat. I don't know. Is that even a B flat? That I know when that's on your thing, that makes the song harder, right?
That's true, it does.
Or you got the hashtag symbols. Yep.
There you go.
That's why everybody plays that one song in church, because it has none of those. Exactly. Thank you. Sang it yesterday. Every single 16-year-old boy knows how to play that song. And they're terrified that they're going to be asked to someday. Moving on. So let's go back here. You had a question? All right, now look real quick. Hydrogen carbonates, I'm not going to bother writing that one out because it's still a metallic what? Carbonate. If you see CO3 with a metal and there's an acid involved, you're going to produce CO2 gas. So the only other one is SO3. What do we call SO3? No. Good. Sulfite. That sure looks like sulfide. What's that? Yep, metallic sulfites. and acid. I guess I could have left produce down there. They produce stuff and SO2, sulfur dioxide gas, which smells terrible.
We should make it.
No, we should not. What's that?
Isn't that the stuff at Yellowstone that smells like absolute crap?
Yeah. That's the same smell as rotten egg gas. It's just nasty. All right, now, here's how the AP test will ask this question. The AP test always presents you with like words, sentences, and then you have to write and balance an equation, and then they'll ask sometimes a question. So you would have yada, 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 and then like A, and there'd be I, and there'd be B, C, all the way sometimes through like G. And it's all based on this one paragraph up here. So part of this paragraph might have like MgSO3 plus HCl, yada, 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 yada. Well, one of these questions would say, what precautions? I don't know. Whatever. What precautions should be taken when doing this exercise, or this experiment, I mean? All right, goggles, apron, and they're looking for one huge one or you'll get it wrong. Nope. This experiment must be done in the fume hood. If they throw in a sulfite, they're looking for you to tell them it needs to be done in a fume hood, so you know that that gas smells. Sulfites break into sulfur dioxide, which breaks into you crying and barfing. So put it somewhere else.
Are sulfites even like dangerous?
Wait, where does the gas in the fume hood go? Does it go up?
That can be dangerous to you. That can cause you to pass out.
Does it like just leak out onto the top of the roof and then just disperse?
If you're over there, look at the school and you'll see two really tall blue towers. They go up there and then they disperse. I taught my wife this over the weekend. I didn't know that people didn't know this. But here you go. Here's the Great Salt Lake. Here are some mountains in Salt Lake. And there's a huge smokestack right here. Everyone know that smokestack I'm talking about down in Salt Lake? I was telling my kids, and they're like, why is it so tall? And I said, the taller the smokestack, the more dangerous the fumes that come out of it. And my wife didn't know that. Now, if you didn't know that either, you should know that, by the way. Danger is directly related to height of smokestack. Are we good?
How do you feel you're helping with the inversion?
Me? I don't actually burn this.
You're helping like cause the inversion with your chemicals and
Maybe
ABA and
how to
stuff.
tell
I'm so sorry.
if the gases released in the smokestack are acidic or not?
It's high. So campfire, we don't have a lot of. Campfire, safe. Refining copper, bad. Okay? Anyway, moving on. She taught me something right after that. She was talking to our sons about where she went. She went to Union High School. And who's ever thought about that name? Not me. Well, Union High School, I've always known this. This is a complete waste of your time. But it's right here. Hold on. That's a really good California. That's not California, but it kind of looks like it. I'm going to write two things that I can't spell. I can spell this one. This is Uinta County, and this is Duchesne County.
That's gotta be the worst.
Well, Uinta High School is right here. Like literally, the football field's in Uinta County, the building's in Duchesne County, and it's called Union because it united both counties. Who would have known that? So she taught me about smokestacks, and vice versa. Yep, life's great. I feel like we're both smarter and that I wasted most of your day. All right.
Well, I did learn something in my AP class.
Good.
Union joined 2 parts of Utah.
There you go. Yada, yada, yada. If you do this, you won't be very popular because it stinks. All right. So the last one we need to add is sulfides. So sulfides, and carbonates. This one, it's just the same. It's a different formula, but it stinks really, really bad again. So as far as gas forming reactions, it's not super hard to memorize. Sulfides, sulfites, and carbonates. So S minus 2, SO3 minus 2, and CO3 minus 2. Those are your 3 anions that produce gas when they react with acids.
Is there a reason they're all -2, or is that just
Well, they are all minus 2 because of how they share electrons, but that's not why they stink or anything like that. It's just by chance. Okay, this is a whole different ball game now. An oxidation reduction reaction. An oxidation reduction reaction is where we have electrons moving from one place to another. And we're going to spend an entire chapter on this. It's chapter 20, I think. It could be 21. We'll spend way more time on this. This is just the scratch the surface version. An oxidation occurs when an atom or an ion loses electrons. Who is always the loser? A metal. A reduction occurs when an atom or ion gains electrons, and that is always the non-metal. Now, this is a little bit tricky because we're going to violate that rule once in a while in oxidation and reduction reactions, but you'll be okay with it. All right? The simplest form of an oxidation reduction reaction I can think of is when sodium solid reacts with chlorine. Whoops, that's a G. It is supposed to be a 2 also. Chlorine gas to produce. Oh, let me just get this picture out of the way. Okay, how about I just do this to you then? I don't need you. All right. We all know it produces NaCl. Now, sure, I'd have to balance this, right? All right. So here we have sodium solid plus chlorine gas goes to NaCl. Well, in NaCl, we know this is an ionic bond between an Na plus and a Cl minus, don't we? Like, I kind of hope we do. This ion is attracted to this ion. Well, how did this become the Na plus ion? It loses an electron. And once it loses an electron, it becomes Na plus. All right, well, how did the chlorine become chloride, or how did it gain an electron? It took that electron that sodium didn't want in the first place. So this lost and this gained, or we're going to introduce some words. Sodium was oxidized and chlorine was reduced. The oxidized is always the loser. The reduced is always the gainer. And it's really simple when it's just a metal and a non-metal forming an ionic substance. But it can get a lot more complicated because we're in AP, so let's make everything suck. All right? Now, you do need to know that you can't have oxidation without reduction. You can't have reduction without oxidation. You have to have one of each. All right? Now, we're going to introduce this idea, and we're going to get okay at it, and then we're going to forget about it for months and months. And most of you will have dropped the class by the time we get back to this anyway, so whatever.
You don't know what people drop the class last year?
No, hardly anyone.
What about the year before that?
Tons.
You said that last year was no fire.
2 years ago, they were idiots. 2 words right here. Okay? Enough said. If anyone knows him,
That's pretty harsh. I mean,
it's not harsh enough.
straight up name dropping right in front of the entire class.
Sorry. It happens.
Message Chase on Facebook, be like, yo, you need to straight protect your neck because.
No, he'll be proud. Be like, oh yeah, I remember making his life hell. I loved it every second. Okay, here we go. Oxidation numbers. To determine if an oxidation-reduction reaction has occurred, we assign an oxidation number to each element in the neutral compound or charged entity. Okay, there's a bunch of rules here. You ready? Elements in their elemental form have an oxidation number of 0. Super easy. So Na plus Cl2, their oxidation numbers would have been 0 because they're in their elemental form. When chlorine is diatomic, it's still considered its elemental form. Okay? The oxidation number of a monatomic ion is the same as its charge. So over here, Na plus, so what's its oxidation number? It's a 1. All right? Cl minus, whoops, they're supposed to be together. Ignore the plus. It's a monatomic ion, meaning not polyatomic ion. So it's a -1. Are you okay with that? So these two are easy. The elements are 0. The ions are just what they should be. Next, nonmetals tend to have negative oxidation numbers, although some are positive and certain compounds are ions. I wouldn't write that whole sentence. I wouldn't even worry about that one really. Just know nonmetals are usually negative. Next, oxygen and hydrogen. These are the two things that will run life for us. Oxygen has an oxidation number of -2 pretty much always, except we're in peroxide, which we rarely deal with when it's a -1. So if you have to memorize something, memorize oxygen is always -2, because we're going to use that to find out what everything else is when we're at a loss. Hydrogen is a -1 when bonded to a metal, and +1 when bonded to a non-metal. Memorize it's -1. It's a +1 in like NH3. Okay? But we don't deal with it being a +1 very often. So we have 4 basic rules. We have that atoms are 0, ions are their charge, oxygen's a -2, hydrogen's a +1, and that can help us figure out just about.
Is that a negative one?
That's what I meant. Thank you. A negative, no.
I thought you told us.
I want it to be a +1. Hydrogen is hardly ever into a metal. I expected this to be written the same order as the other one did, but it did not. Sorry. +1 is what you need to memorize H as. Yes, sir.
So,
Am I emphasizing this enough?
You're skipping over a lot of crap.
never mind, I forgot what this
I feel like I didn't give enough notes, but if it's just kind of like a stretch, then you're doing great.
All right, good. The rest of this can pretty much be figured out. Like, you should read this if you haven't already, but you should already have, in my humble opinion. Fluoride is always -1. Halogens are always -1 except for when they're not. How about that? The sum of oxidation numbers in a neutral compound is always 0. That's a huge one. The sum of oxidation numbers in a polyatomic ion is the charge of the ion. That's a huge one. I don't care. I just want you to be able to use them. So what we mean in this NaCl is that the oxidation numbers at the top had to add to 0, which made sense. +1 -1, that equals 0.
Isn't it just with everything? The sum of oxidation numbers?
Not necessarily. Like, yes, but you do need to know if you just have a polyatomic ion, you put its charge, like SO4 equals a -2. So let's actually look at SO4 and use our rules to figure out what S and O are for their oxidation numbers. All right, so S, there's not a rule that tells me about S, but there is a rule that tells me about O. What is it? That it's -2. To find S, this is what you do. You take 4 times -2. What's its total charge? -8. Something -8 equals -2. What's that something? It's a +6. So the oxidation number for sulfur in SO4 is a +6. Let's try that with NO3. Tell me the charge of N. Because that's the charge of NO3. This is a polyatomic ion. +5. Now here's my question. Is oxygen's number -6? No, it's -2. We just used the -6 to find out how to make this plus that equal a -1. I feel like no one will have any idea what I'm doing here. This is just talking about what we just did. All right, we will end right there. We're about 10 minutes behind. Please read all about oxidation reactions tonight.